my goal is to sort of build Shor's algorithm using Quirk, but before that, I want to check that there's one bit of intuition that I want to check that is correct, and I have to check it with the Q experience, because it's about this thing here. So it's really about that part of the of the circuit which is kind of was the biggest. And I know that I made a rant about that, and then I said that I won't build that, but I kind of think I really would like to do that, and it's about the kickback effect here. So that's what I want to test. I have an idea of how could that work, but I just want to test quickly that it works. So I'm going to see if I can do that with quantum experience first, and basically because of the flexibility with parameterization of rotations, because here in the Quirk I can't figure, I haven't figured out yet how to can I make a simple parameterized per angle kind of. So what I want to do is the following. If you go back and check my videos about the phase estimation in Shor, that's what my point at the end of the whole kind of process was that what this is really doing here is a phase kickback. So it's doing a multiplication, it's doing an exponentiation modulo something like what you see in here, right? So to the power of 0 mod 21 is 1, 2 to the power of 1 mod 21 is 2, and then 4 8, right? And then it's about finding that cycle, because here it kind of repeats. So what you want to do with phase estimation here is you want to encode those results to 1 2 4 8 16 as relative phases in the superposition, but you want to do it in a way that you end up drawing a sort of a wave encoded the interface, so you can then, using the QFT, find the period. And the way I'm smelling the way you do that is you need to translate that. So if your modulo is 21, right? Well, let's make a simpler example. Let's say your modulo is, for whatever reason, 8, right? So 8, to represent the 8, you need 4 qubits. So it's like with 3 qubits you can go up to 7, right? And then if you add 1, it would just overflow, and then kind of you're back at 0. So that, it seems to me, that simulates a bit the modulo part of the whole thing. So what I would assume is that any number that goes between 0 and 1, you can then represent in the phase if you do that in relation to, like, proportionally to 8, right? So for example, 4, right? If it's 4, because you're doing modulo 8, so you're at between 0 and 7, right? So 4 is a 50% rotation. So it's like a rotation half the way of your phase. You know what I mean? So then when you're back at 7, it's like almost like 100%. It's almost like a full rotation. So when you're at 8, you're back at your like 360 degrees or 0 degrees. So that's kind of what I don't know if this is the way that it's done. It's probably there's a way more efficient way to do that, but it's what I want to test today. So what I want to do is, and I want to mock the exponentiation, because I don't know really how to do that yet. But I'm going to use those 3 qubits as my basis for the numbers for the whatever exponentiation, and that one here is my register for where I want to encode the phase. So the first thing that I will do is I'll put that into superposition, because that's what you do here. Now what I say is I'm going to mock the way I'm going to mock it is I'm going to just hard code the result. So this means that we're not going to make here like an exponentiation, but let's assume that we do an exponentiation here, or that we've done it before, and let's assume that our result is like 0 0 1. Sorry, no, let's do 4, like 1 0 0 is 4. So we want that to rotate. We want now the phase to rotate. The phase here to be not blue but yellow, right? So in this case, what this tells me is that I should have a rotation on Z here, a conditional, like control Z between these and these of not a conditional rotation in Z, because now I can specify the angle of pi, right? So that's what I want to have. But is it what I want to have? Because now I would like this to be yellow, because I know it's halfway through. So, but if I do 2 times pi, that's kind of yellow. Yeah, that's yellow. So what it literally means is I'm giving that exactly. So, and now I want, so I've done 2 times pi. So ideally, if my result of the operation would be that, so that's a let's say that's 6. Yeah, of course, that's 6, right? So I would like that to be. So this is basically 6. So if I make that proportional, right? 6 over 8 is like 75. So 75% of 360 is like 270 degrees. But if I'm now expressing it in terms of pi, so it's 0.75 times, I assume a full, for some reason, because I am most confused, it seems like a full round is 4 times pi for whatever reason. So 4 times, so 0.75 times so let me see, maybe I should pull out the calculator. That is me. So 0.75 times 4 times p, I'll say 15, so it's 942. So that would be this means that conditional to that is a 9.42 rotation, kind of, yeah. And if I would add these, right, so I would now have a 7, and I now basically if I do 7 over 8, right, this is like 87%. So if I do 0.87 times 4 times 3.15, this is like 10.92. I don't know if I'm doing this correctly. 10.92. And that's now, so if I now say, no, I just have 1, right? So you see the problem here is that I don't know, I can't tell what the phase is here, up here, with this composer. I really can't tell what the phase is. But you understand what I'm doing, right? So my theory here is that that basically you would rotate proportional to the number. So you would rotate proportional to the outcome of your operation. If your operation is an 8, right, then you're kind of you're kind of purple. It's impossible to tell here the face. That's a big problem. So you will be kind of proportional to almost being blue again. So I'm assuming it's kind of correct. Whereas if you're like 0, or your result is, let's say you have another qubit, right? And then your result is like, in this case, like these. So that's not. I would expect that to be not rotated at all. Because I want zeros. Is this affecting anyhow? I don't think so. You know what I mean? But I don't know how I can check that. How can I prove whether what I'm doing correctly or not? I mean, no. What am I doing? Oh, this is this. This is this. I mean, it doesn't matter. But it's like if this is 1, then it's kind of orangey. If this is 2, then it's a bit more orangey. If this is 3, because this is wrong. Those numbers here are wrong. This should rotate in proportion to its weight, because I should make a rotation that is proportion to the weight of that qubit, right? If this is a 1, let me see if I can do it this way. So this is if this is 1/8. 1/8. Is that correct? Yeah, 1/8 is 0.0125 times 4 times 314. It's 157. So let's say this is 157 exactly. Kind of makes sense. Yeah. Now here, this would just this is 2. So 2/8 times 4 times 314 is like 314. 2/8 times 4 times 314. Is it 314? Okay, yeah. 315. Is this with a dot or with a comma? And then, as we said here, so this is 4, right? And then, so 4/8 is 0.5 times 4 times 3.14 is like 628. Makes no sense at all. That makes no sense at all. What if I clear that. If I add 1, 2, 3, 4, 5, 6, and 7. You see what I'm trying to do, but I think I'm doing that wrong. I think I'm getting that wrong. But it's kind of, I'll get it right. I'll get it right at some point. But you know what? So it's so the idea here is that if I would then add those, right, you would get almost a full rotation. Because that's how you want the face kickback to come here. That's the concept. That's the concept. Because if I check in here, that's the way. So I think this was here. Face kickback. Yeah. Register 1, exactly. That had to be 1 for this to work. Yeah. So that was my idea, but it doesn't seem to work as expected. Doesn't seem to work as expected. Maybe. So what if I do the halves of this? Because this 4 times pi is what confuses me. So 157 divided by 2 is 0.78. 0.75. This is 314. 314 divided by 2 is 157. And 628. 628 divided by 2 is, of course, 314. I'm so stupid. 315. No, it's not. Doesn't feel right. Doesn't feel right. 0 should be 0, so this should be blue, right? Why is it not blue? If there's no 1 in here, why there's no, this something's wrong here. But you see what I'm trying to do, right? I mean, I'll get it right. I'll probably do another attempt in the next video. But I think I'm not sure why I'm getting. So for me, that doesn't make sense because you shouldn't be getting anything at all. I mean, it's a controlled rotation on Z. Why is the face changing at all? Right? I always assumed that no matter what you do, that should stay like that. Because this a 1 in here, but then nothing happens. Or does it? Because there's a 1, so there's a face rotation here unconsciously. there is. And if I do an X here, it seems like it's the same phase. You know what I mean? But then there has to be something else used here instead of a controlled rotation. Thinking. Because the control Z, because you see the control Z doesn't do anything in here. So why does the control rotation in Z do anything at all? That's what I'm asking. Whereas if I add a 1 here, bam, bam, now you got it. Now you got the phase kickback. That's what I'm talking about. So then there's something wrong with the control rotation here, which is then definitely not what you want to have. Because what is so what if I do 2 times pi? Yeah, then it's yellow. But what if I just do pi then? What if I do pi divided by 4? Pi divided by 8. It's almost blue. Pi divided by 20. And now it's kind of almost blue. But it's because I've done a really small rotation. What if I do 0? Yeah, now it's blue. So yeah, sure, if you don't rotate, of course. But then if I do 4 times pi, it should also be blue. Yeah, okay. Okay. Yeah. 4 times pi. But it's nevertheless acting despite the fact that this is 0 here. That's what's confusing me right now. Whereas a control Z, right, doesn't do anything. And it should literally flip that. It should flip but it doesn't do anything. So that's that essentially. And again, that's the same problem that I had with the control Y and the rotation on Y. Because I think that's the no X Y Z. I don't know. That's confusing me now. That's confusing because in Quirk you have something here, which is basically what I think that's happening. What I think that these parameterized gates do is rotate the target by input A. So if I would put a Hadamard here, and then I would have like say here like say that I have 6, right? So it's 110. And I say that this is input A. This is input A. And now I'm doing this rotation. So you see, this has rotated. But how much? I assume that's... Okay. And if I add another X, Yeah, then we have done almost half the interesting, because if it's nothing, if it's 0, then it's 0. Then if it's 1, then it starts rotating a little bit. If it's 2, it rotates a little bit more. If it's 3, it rotates a little bit more. If it's 4, right, then we're in the half. Okay, so that's exactly the effect that I'm trying to achieve with the quantum. That's the effect that I'm trying to achieve with the because essentially you're encoding in the phase here. I don't know if you can see that with the chance, the density, the blocks here, the amplitudes. I think I can only see that with the amplitude display. Oh, no, I think I can only see this with the not the sample, the amplitudes, really. Yeah, that's kind of what I'm seeing here, right? If I have another one, which I kind of move here, and this is these, and this is here, and then I use another input A here, so there's a 3 more, right? And I do a 1 here and a 2 here, right? And then this is a rotation here. And then I see a amplitudes. So as you can see, and that's what I'm trying to achieve, right? It's like here. So this here represents a 1, and you can see that it rotates the face a little bit, and here represents a 2, so you can see that it rotates the face a little bit more. So you're kind of encoding in the face, you're encoding those results, and that's kind of that shows the effect that basically shows what this is really doing here, right? It's kind of creating that wave inside of your phase, inside of the phases of the superposition. Bam, 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 bam. So then the QFT can act. But basically, I'm trying to reproduce that, because here you have the building blocks. You have the input, and you've got this rotation, these parameterized rotations. But I'm trying to implement that with the IBM Q-Experience, and it doesn't seem to work completely, because maybe I just cannot do that, because it seems like the control rotation is not what I need. Or it's not giving me, it's making another, it's sort of doing another thing. It's not what I really expect it to do. Maybe that control rotation is not what I need. I have to check how is this defined. That's probably going to be my next step. I really want to do this here, because I want to really see how that would, then unfold. But that's basically it. So I think I'm on a good path. That's, it's kind of first step. I want to try to understand really how you would ideally build that. Sure, here we're just making a number, but what you need to do instead of making a number is you need to make a multiplication. And in Quirk, you have already the modular power multiplication gate, which is kind of doing that for you, and it's not what I want. I mean, I want to see how that is built inside, kind of. But this is what you wanna. This is what you're trying to do. And now you do another one. So you can see it requires a lot of qubits, actually, right, to do that. Okay, cool. So yeah, basically that's it. But it's, you see how awesome this tool is. I mean, that's an example of how many insights you can get, because you can see the faces, and here I cannot see them. I can see only the colors, and that's difficult to then figure out where am I in color spectrum. Am I closer to blue, closer to yellow? So, but I think I was not kind of far away. I think it's not that I have to give it back to blue, but I can stay in yellow. I don't know, because it feels like this is also just rotating until the half, until the opposite. So I don't know. We'll see. We'll see. I think I'm kind of getting there step by step. Cool.